Alright, so in this video, I'm going to be showing you one of my favorite Yusuko problems as of lately. It's called 2019 Yusuko Sleepy Cow Sorting from Contest Bronze, and this isn't a hard question by any means. I just really liked the problem. Like, once you come to the realization, you're like, oh dang, that's actually really cool. And it's easier than it looks, right? So basically, this problem is you have a farmer John. You have N cows, like pretty much in virtually every Yusuko problem. You have N cows, right? And these cows are going to be lined up with Farmer John just standing somewhere. The position of Farmer John doesn't matter, but the positions of the cows relative to Farmer John do matter. So in this case, they just make for the Yusuko basically just gave us this example, right? If n is equal to 4, so we can understand the problem more. So if n is equal to 4, Yusuko showed us that we can have cows 4, 3, 2, 1. And 4 is the cow next to Farmer John. So this cow is the only cow that can move along the array. Because our end goal is basically to transform this array into its sorted form. So 1, 2, 3, 4. But the restriction of doing this, the caveat is that you can only move the cow that's paying attention to Farmer John. And the cow that's paying attention to Farmer John is logically and stated to the in the question is the cow that's directly next to Farmer John. So only 4 can essentially move in this array. And the restriction is that you can only move this cow k places down. So if k is 2, if you move this cow k places down, by the way, k in general is in the range of 1 to n minus 1. If you really want to be this formal, you could say k is an integer, but like, come on, this isn't math. But if you move k places down, what happens is that you jump here and you jump here, and then the new array is 3, 2, 4, 1. So that's basically their example to show you what k places down. And you want to keep doing this, right, until you get this sorted array. And you don't actually have to like end up with a sorted array. You just need to count the amount of operations, and that's the neat little algorithm we'll find out after experimenting with this problem. Now, just to make sure this cow can only move k places down and so on. And actually, the value of k is irrelevant. Well, it's not irrelevant, but you don't actually need to find k after every operation. That's honestly sometimes Yusuko problems try to give you more than you actually need. You don't really need to get caught up that k has to be restricted in this sort of range. It k does not matter, and you'll see why. So let's look at the test case. So unfortunately for the test case, they don't actually like explain anything, and you'll know why they don't explain anything because the solution is pretty simple and essentially like explaining the test case just gives it away. Like if they were to explain it, they would just say the reason why it's 3 is because it's 3. If they elaborated, it would give the solution all away. So that's why they didn't give an explanation. Once you realize the solution, you'll understand why. So n is equal to 4, and we have these cows with Farmer John here. It doesn't really matter where, it's just relative that matters. So we have these cows 1, 2, 4, 3. And we want to somehow transform this array 1, 2, 3, 4 this array to 1, 2, 3, 4. And our restriction is that only the cow next to Farmer John can move k places down. So the k places down don't matter actually. The idea is that you want to find the smallest, or not the smallest, you want to find the largest array, or subarray, I should say, the largest subarray at the end. Like you want essentially, so you want to start iterating from the end, and you want to dynamically, not it's not necessarily dynamically, but like you want to linearly find the smallest subarray that's already sorted. So the largest sorted subarray, I should have specified because obviously largest subarray at the end would just be the entire thing. Like, but you want to find the largest sorted subarray. So we start from the, and you'll see why. Don't worry, you'll see why. Let's just first find the largest sort of subarray. Don't worry, I got you. You'll understand why it's a largest sorted subarray. But the idea is that we find this. So we're like, okay, we start from the end. We're like, is 3 sorted? Yes, it is. Okay, so then we try to add 4. Is 4 sorted? Well, is this array subarray sorted? 4, 3? No, it's not. So the largest sorted subarray at the end index is simply just 3 itself. And then after that, the idea is that you can essentially move all these cows to their sorted position. Like, what I mean by this is that, look, think about this intuitively, right? If I have this sorted array, what I can do is I can move one into its, I can insert it into its position. So I can move one here, and then I can have two and four. Then I can insert two to its position. So one, two, three, and then I can insert four into its position. So the idea is that the subarray we're choosing is already sorted. So if the subarray we're choosing is already sorted, then there's always going to exist a k such that you can essentially move the cows that are not in the sorted subarray to their respective places, right? For this one, the k still happened to be 2, but we don't actually care about the k. We just care that there exists a k such that when you consider cows that are not in this largest sorted subarray at the end, when you consider those cows, then you can move them in one move, because that's the idea. So let's just do another test case so you can understand this. So you might think that the answer is n minus 1, but it's not. It's actually n minus the length of the largest um subarray at the end. And I think that's called a suffix. I'm not, I think, yeah. Largest subarray at the end. Okay. So you basically, it's n minus the length of the largest subarray at the end. And it's obvious because for here we're just there's always going to exist a case such that we can move it down because it's already sorted, so we don't have to worry about, we can just place it, you know what I mean? So let's just do another case so you can understand this a little bit more, because this case is the fact that it's n minus 1, but there will be at most n minus 1. There can actually be less because the subarray at the end is only going to increase. There's always going to be a sorted subarray at the end. Albeit it could be 1. So let's just look at the case where it's like 1, 1, 4, 2, 3. So we find the largest sorted subarray at the end. So we check 3, is that sorted? Yes. We check 2, 3, is that sorted? Yes. We check 4, 2, 3, is that sorted? No. So it's 2, 3. And the idea is that I can simply just insert 1 into its position and insert 4 into its position. Because after I insert 1, 4 can freely move k places down. So that's the intuition. So now we just have to see how do we implement this. And it's actually a very easy implementation. So let's uh let's do sleepy. So this is a very simple implementation. Like the main chunk of this problem is just to notice that, and it's actually not that easy to notice. In fact, I actually got very distracted about this k cows and k places down. So like I made a function that transforms an array if you move the cow next to Farmer John k places down, and I realized, wait, I don't need this. I can just do um this algorithm. It's not really an algorithm, but this kind of little neat trick. So yeah, sometimes you just have to play around with some solutions and see if you can get a very smart way to doing stuff. I'm sure that might have worked using a function that actually simulates the k places down, but then how would you choose k in each operation? That would be hard to think about, and brute force is a little bit um convoluted there. So let's just do this. So we're gonna just quickly implement through this. So throws IO exception. Bro, did I just do that lowercase? And then we're gonna need buffered reader, and then we're gonna need br is equal to new buffered uh buffered reader, new input stream reader, and then that's system dot out. And then we're gonna need print. So we're actually not even going to need any functions here. That's the thing. We're not even going to need a function. Like the implementation is really simple. You might get confused with the minus ones and stuff at the end. Those are pretty easy to debug anyway. Like I had to debug some minus ones, some plus ones. The typical minus ones, pesky minus ones, and stuff like that. So system. Did I just put system.out? Okay. I'm obviously not okay today. So this is I'm bringing okay. I'm bringing in. Okay, Riplet is extremely slow, so just give that some time. Why am I using it? Good point. I'm lazy. Okay, so new string tokenizer, and I already made this up. Like I already did this problem, so like okay, yeah, read line. I don't really know why that's broke. This is really annoying. Let's just refresh the page because I hate like it's it the IO the file input syntax. The syntax is right. I just hate Riplet. Like that really pisses me off when they put a line when you know it's correct. There's no errors. Like it takes forever to get off. So yeah, but we're just gonna implement the solution. In fact, you can probably it's probably so easy that you can click off this video and just implement it yourself. So we're gonna take in our input n, which is just easy. We're just gonna take in n. So int n is equal to integer dot parse int st dot next token. And then here's how I take in these types of inputs, like if it's like a line, because if you try to take it in as an array, you can't. Well, I think maybe you can, but I just do this. Basically, I read this as a string first. So I do string line is equal to I do string line is equal to br.readline, and basically after I do that, I create an array called transfer, and I hate this line over here. And basically what this is gonna do is that it's just gonna split by space, and then what I do is oh my god, this line, stop doing it. Oh, I'm having a pet peeve. It's a pet peeve. Okay, thank God. Okay, so for int I is equal to 0, I to n, and then I plus plus. Then basically I just parse. I make a. I'm obviously gonna make a new array. You know, it's the new array is gonna call cow. So in cows, right? The basic, most basic. So cows, that's gonna be sized to n because there's n cows. And then basically what I do is I loop through each thing in the transfer, and I simply what I do is I'm just saying cows at I is basically equal to integer dot parse int. So I'm transferring everything to an integer. That's why I called it transfer, and that's how I take in those types of inputs. You might take it in a little differently, but it really shouldn't have any effect on the problem. And yeah, that's basically what you do, and you can check if um and you don't need a string tokenizer here, like you don't need one. So now the idea is that we just need to find the smallest the largest sorted um the largest sorted subarray at the end. So what I did to do this is, by the way, this thing is just annoying. Cannot be resolved to a variable. Don't worry, it's a Ripple just being bad. So what I usually do to do this, well, we're just gonna iterate from n minus one, right? From that n minus one index, and we're gonna go to the 0, 1, and we're just gonna do I minus minus. And then after, what we're gonna do is we're gonna basically just check, because in order for this to be sorted, each successive element, maybe iterate from the backward, has to be smaller. So essentially, or this one, so when we iterate backwards, 3 has to be bigger than 2, and then 2 has to be bigger than the next one for it to work. So not smaller. Each successive thing has to be. Oh, this is really getting on my nerves, dude. Okay, Ripley, you're so bad. Okay, this is I really need to use something else when I'm doing videos. So basically, we just each thing has to be bigger than it was before. So cows and um cows and I just have to be bigger than cows at I minus one. Don't really worry about this. It won't go out of bounds because I'm gonna have something called int sublink, which is just the okay. This thing is really annoying me. This red thing. I'm sorry. This red thing is annoying me, dude. Stop this nonsense, Ripley. You're trash. Okay, so we're just gonna have like this variable called length, and what it does is that it's just gonna store the largest subarray length. And if this is true, then we can just increment this, and like else we can just break this. Like we can just say else break, and here's the thing: you don't actually have to rate because you might be like, oh well, this I is gonna be zero, then Cal's at -1 is gonna crash. Well, no, in all the test cases and logically, you don't like it's you're never going to reach to zero, so it doesn't really matter. Like if you think about it, you're never gonna reach to zero. So that's essentially it. And then once you get that sub length, you actually have to add you have to so at the end you have to do so the answer is equal to n minus that sublink but then also minus 1 because the sublink is only considering cows after n minus 1 like right we check like and you could just debug this. It's very easy to debug, so if you're worried about like, oh, do we need a -1 at the end, just debug it. But like, you're only considering like these cows. Like for each increment, you're saying is 3 bigger than 2. It is, and then that's like +1, and then like it's just +1. Like you'll figure out the -1. It's just that's the thing you can just figure out, and then you have to do answer, and then after answer, you gotta close your code, and then we gotta test if this bad boy works. I might have a bug I don't know. Maybe I have a bug. Maybe I do. Maybe I have a bug without knowing. Maybe I have that out of bounds exception. Maybe who knows? Maybe that break doesn't work. Why is this not? Why is it even? Why is it not like weird? Oh, I did this in the for loop. That's kind of cringe. It's kind of cringe. I'm not gonna lie. That's kind of cringe. Okay. I was like, what is it? And I was like, oh yeah, the prints in the for loop. Yeah. Okay. Yeah, that's kind of weird. Bracelet's weird. This is like okay. Maybe I have a. I don't think I have a bug because maybe I do. Maybe I have a bug. Who knows? Maybe I have a bug. You never know. Nope, I don't have a bug. So that's our answer. I'm gonna submit it to Yusuko again. Actually, to be honest, I'm not going to submit it to Yusuko because, like, as you can see, I already submitted it to Yusuko, and this is the code. It will work. Um, for example, let's judge it against 1423. This is supposed to be the answer here is going to be 2. So if you do it, it should be 2, 1, 4, 2, 3. So if you don't believe my code works, let's just test it for our own input custom test case. Because this is the algorithm, you can also check the solution. But 4, 1, 4, 2, 3. Here we go. So that's how you do this problem. It's a pretty neat problem. And yeah, see y'all later.